Now the second part of the video is on electric field. It's the same lecture, but the second part of the video, and it's about electric field. Um, so first, we're gonna define electric field, just like magnetic field. We can define an electric field around the charged particles, and then we're going to talk about electric field due to a point charge, electric field due to two dipole charge, electric field lines, and force and torque due to a charged particle in electric field. So these are the topics. So first of all, again, go back to Coulomb's law. We have to slightly modify Coulomb's law now in electric fields. So Coulomb's law simply says actually the force of attraction or repulsion between two charged particles is given by this formula, right? But it doesn't say actually why do they attract or repel, and so it just gives you the force at distance, right? But nothing can travel faster than the speed of light, which is this, right? 10 to the 8 meters per second. So how do they even sense the presence of each other, right? How do they exert force on each other? Then you have to modify. So this is the different version of electric field, is simply the different version of Coulomb's law. So then the main idea is, first, if you have charge q1, say, right, if charge q1 and q2 are separated by some distance or in space, first the charge q1 generates some electric field in this invisible force field, invisible field, just like magnetic field generates magnetic field. Charge generates electric field, the invisible, you can't see that. First, charge q1 generates electric field, and this electric field then exerts force on the charge q2. That's how charge q2 find the presence of q1. So that's how it works. So the main idea is, if two charges are separated by some distance, so they will communicate, they talk to each other through the electric field, right? Because first charge generates electric field E, and that electric field actually then exerts force on charge q2, and vice versa actually. So the definition of electric field is the mathematical definition of electric field is just the force experienced by the test charge. Q naught is a small test charge placed at that point, because in order to feel the force you have to put a small test charge. Test charge is just like a sensor, right? And its standard unit is newtons per coulomb, because it's newtons per coulomb. Coulomb is the unit of charge. That's how, this is the mathematical definition of electric field. Electric field is force experienced by a test charge, right? Q naught is a small test charge. It just serves to allow the electric force to be measured, right? It doesn't do anything. The test charge will just allow force to be measured. So then let's calculate let's derive the formula for electric field due to a point charge. So this is your main charge, this is the charge, and we like to find the electric field at point P at distance r. So what would be the electric field at point P? So, well, first what you need to do is, first you have to put a test charge. Remember, this Q naught is a test charge at given point P, and feel the force. And this is the force, right? From Coulomb's law, this is the force of attraction between these two objects, right? And then divide by the test charge. That's by the definition of electric field, right? Because it's the force felt by the test charge, force over the test charge, and q naught will cancel out, right? This q naught and q naught magnitude will cancel out, and then you will end up with this formula. And this is the formula for electric field, magnitude, I should say magnitude, because so this formula will find the magnitude of the electric field at given distance r due to the given charge, right? Due to the given point charge q. So that's the formula for electric field. And electric field is a vector quantity, right? Definitely, electric field is a vector quantity, because it's a force felt by a test charge. And test charge, for a test charge, is always, for this sign convention, we always take the test charge as a positive test charge. So test charge is always positive. So then, if you have a positive charge or bunch of positive charges, what's the direction of this invisible field, electric field direction? So then, for positive charge, it's radially outward. Why? Because if you bring a test charge, right? If you bring a test charge at any point, this test charge would feel a force of repulsion, which is directly away, right? Radially away from this charge. That's why for a positive charge, the direction of electric field is radially outward. And if this test, the same test, if you bring it towards a negative charge, right, it will attract, the test charge will attract towards the negative charge. That's why the electric field for negatively negative charge is radially inward towards the charge. So these are the electric field definition. Okay, so this is the electric field pattern, right, for a single charge around it, and this is the electric field pattern for a negative charge. So here's more example. So say this is a source charge. It's a big charge, right? It's a source charge, and if you want to find, say, if you put a test charge, let's say test charge, any charge, small charge at this distance, right? So what would be the force on this charge, right, due to this charge, right, this electric field? So and which is given by y. Why? Because of this. Because electric field is different by definition force per charge. Then force will be Q times C. So that's how you can find the force on any charge, right? Force on any charge placed in the electric field in terms of electric field. So E is the electric field. So E is the electric field, right, produced by this source charge. So then, so here's the conclusion. So say this is the electric field. It may not be parallel. It may not be uniform like this. So if you place any test charge, right, any charge in the electric field, vicinity of electric field, this is the force felt by the positive charge. The force felt by the positive charge in the electric field will be in the same direction as the electric field. But however, if you put a negative charge, obviously, the force experienced by the negative charge in the electric field will be in the opposite direction. Why? Because you are putting a negative charge. Its direction, the force on a negative charge will be opposite to the electric field. And here's some example, right? You can calculate, now using this formula, you can calculate the electric field at any point actually. So for example, proton, this is a hydrogen atom for simplest example. So what would be the electric field exerted by proton at electron, right, at this distance? So if you know all this distance, you can simply calculate that. And these are some the strength of the electric field, in various cases you can check it. So from very small field to very large field. And again, what happens if you have bunch of charges now, right? If you have, instead of just 1 point charge, what happens? How do you calculate the net electric field if you have bunch of charges? Then that's why we need a vector addition. So then you first find, just like I showed you in a previous video, vector revision. So first you need to figure out the net field in x direction, net field in y direction, and if there is z direction, and then figure out and the net field. So here's an example. So this is called principle of superposition. So you have a positive charge, you have a negative charge, right? This is also called dipole. So how do you find the net electric field, right? Remember, net electric field, right, at that point. So then you have to do one at a time. So first, the positive charge, what's the direction of the electric field due to the positive charge? So this is E2. This is the direction of the E2, right? This is the electric field produced by the positive charge, which is away, right, away from the positive charge. And the electric field due to the negative charge will be towards the charge, towards the negative charge. Remember the sign convention, right? And then since these are vectors, so what would be the net electric field? Well, then the net electric field will be the superposition, right? Superposition. If you do the geometrically, if you just draw the parallelogram, then the net electric field is given by the diagonal of this parallelogram, right? Which is just the vector sum, which we can do vectors. So here's some quick question that I will be asking in the quiz. And there are some more examples of electric field patterns. So here, if you have a dipole, this is dipole means two equal and opposite charges separated by some distance. This is the electric field, just like magnetic field. This is the electric field pattern around a dipole. It's different at different points. It's different at the magnitude and the direction will be different at different points. But however, if you have two parallel metal plates separated by distance and two charged metal plates, right, the electric field between these two charged metal plates will be uniform like this, right? It's also called a capacitor. This is also called a capacitor. Okay, This is a capacitor. It's called capacitor. We'll talk about that in electricity. So why the electric field within the capacitor is uniform? Uniform means parallel to. Because why? Because you have infinitely large number of positive charges here, infinitely large number of negative charges here. At each point, right? At each point, the net electric field due to all these charges will be like this. The vector sum, right? You have many electric field, but the resultant field will be like this. Electric field due to at any point the electric field will be constant and in the same direction. It goes from positive to negative charge. That's why, because each electric field is due to the contribution from all these, and they will all point from positive to negative direction. And electric field you can actually visualize, actual visualization. You just need some seeds, and it's these seeds actually you have to put in some oil in a petri dish, and then these are the two charge electrodes. So let's say this is positive charge, this is negative charge, and if you leave it for a while, it will this all these seeds will be electrified, and they will settle down, and then they will show the this is for positive and negative charge, right? This is for both positive or negative. Okay, so that's how you can visualize the electric field, and this is the electric field visualization for a capacitor. This is the actual charge. So this upper plate must be positive, this plate must be negative. So then the electric field actually is going uniform, right? We just talked about that, from positive to negative side. This is the electric field actual visualization. And electric field lines are just a collection of these electric field vectors. The electric field vectors, the collection are the electric field lines, just like magnetic field. At any point P, the electric field vector is tangent to the electric field. So for example, if this is the electric field line, if you want to find electric field intensity here, just draw the tangent. And here in this case, electric field is different at different points. The magnitude of the electric field vector is proportional to the density of the line. So you have more density here, electric field is more. And here's some examples, right? I already showed you. This is the electric field for point charges, and this is the electric field patterns for dipole. This is for positive, negative dipole. This is for positive. They will repel, as you can see. And I will be showing some example problems. Next, this is an example of the motion of charged particle. Motion of charged particle in electric field. How the charged particle behaves in electric field. Just like how does a mass behave in gravitational field, right? Gravity. It's a projectile motion. So this is exactly same actually. If you shoot an electron or any charged particle in electric field like this, right? So how do they behave, right? So we're gonna now do some dynamics of it. So actually this deflection of the charged particle actually in electric field is utilized in everyday life in printers actually. Printers, right? Print is because of the electrostatic charge. Inkjet printer works on the principle of electrostatics, and this inkjet printer like deflects back and forth because of the deflection in electric field. So this is the application in printer. So here's the dynamics of electron motion in electric field. For example, in this picture, right, in this diagram, so if you shoot an electron, say, or any charged particle with initial velocity v naught tangentially, right, the original velocity, and when it enters the electric field exerts electric force on the charged particle, and it bends actually, it deflects like this, right, because of the electric force, just like the projectile motion. When you throw a mass off the table, right, it follows this path, right, and this charged particle here must be a negatively charged particle. Why? Because it's deflecting against the electric field. So what would be our job is to find, all right, what would be the net deflection at the end of the plate. So let's say this is d, right? Let's say this distance, this deflection is d, right? So what would be the deflection d at the end of the plate? So then this is just like a projectile motion. First we have to consider the x direction, right, and do some kinematics. So the total length, this total length is L, say, right? So L is then v naught x t plus 1/2 x, but ax is 0 because because look at this electric field. The electric field is only vertical. There's no horizontal component of the electric field, so there's no acceleration, right? Because there's no force in the horizontal direction, so there's no acceleration there. So then you calculate the time for solve for time. Time will be L over V naught, right? V naught is the initial horizontal velocity. And then also find the acceleration in y direction. So how do you find the acceleration in y direction? So acceleration is from Newton's law, total force over mass. And what is force? Force is Q times E, remember. And this is electron actually. So Q E times E, right? Because force is Q times E. E is the electric field given to you. So once you have time and once you have acceleration, then you can find the deflection, the vertical deflection of the electric field at the end of the plate. Then you just need to now solve the kinematics in y direction. So y direction do the same thing. So the y deflection is d is v naught yt plus 1/2 at square, right? But v naught y is 0 because there's no initial vertical component, right? Initially the electron was only traveling horizontally, so this is 0. So that makes it too easy. I mean 1/2 ay is this, right? This is ay, right? And this is the time from here, and that's how you can find the vertical deflection. And we're going to solve many problems based on this. And here are some couple more examples. So the electric field inside the conductor is always 0. When conductors, we're talking about conductors, metals, because it has to be 0 because since conductors are conductors can allow the charges to flow. If you charge a metal, say, right, all the charges will always actually sit or reside at the outer layer, outer surface. Why? Because they repel each other, right? You repel each other, and the charges will always go at the surface, always reside at the surface. So inside the conductor, there's no electric field because there's no charge, right? The charges will always distribute only on the surface because of repulsion. And since there's no electric field, right, inside the conductor, is safe inside. So that is actually used in electrostatic packing actually. So electric field. So if you order any chips, very highly sensitive chips or processor, it always comes with a package like this. So this is electrostatic shielding because it is a metal coating. So if you put a sensitive devices inside this packet, is safe because the electric field inside the packet is 0. Just like this. This is called Faraday's cage. This is a very well known actually demo actually, right? It's called Faraday cage. Right, so this portion inside this cage is completely safe, right? Even if thousands of volts of discharge is thrown to this cage, this portion inside is safe. Because why? The net electric field inside this cage, metal cage, hollow cage, is 0, has to be 0. So this portion will not get any electric shock, And this is how the dipole, the charged particles dipole behaves in electric field. So this is the electric field, right, due to any source. And if you put a dipole, the dipole feels the torque because the force on this positive charge is that way towards the same direction as electric field, and the negative, however, the negative charge will feel in the opposite direction. That creates a torque, and it tries to align towards the electric field, and which is used in many applications, including the microwave oven. And you can see this how microwave oven put food. You can see this animation, interesting animation, because a water molecule is dipole molecule. It's already charged actually, and if you put this in oscillating electric field, which is microwave generates. So our microwave oven generates usually 2 gigahertz, 2.545 gigahertz frequency, which is oscillating frequency. And since the water molecules are charged, polarized charged molecules, it just oscillate, right? It try to oscillate with the same frequency, and that generates heat and that cooks your food.